All right, so today we talked about position versus time graphs that show an object changing its speed. And up here on the screen, I have an example of one where you can see the graph at time 0. It starts at 50 centimeters, and then the position numbers get smaller as time goes on. And this kind of graph represents speeding up, and we can see that in a couple different ways. We talked about how you could see the stiffness, the steepness of this line. It's not very steep at first, but it gets much steeper as time goes on. You could also think of it as the spacing between how far the object gets each second is increasing. And so that motion diagram shows that it's speeding up as well. So a kind of thing that we would have already known how to do coming into today was how to read where a particle is, its position at different times. And so what I've done here is just subtract, okay, started off at 50, 1 second later it hadn't moved very far, it was at 48, another second later it was at 42, and then 32, and then 18, and then finally got back to the origin. And we could put all of that data into a table. So the question we were asking today was, how can we talk about how fast the object is going at specific times? And one way to look at that is to see initially there's not much change in position, so it must not be moving very quickly. But as we look later, that change is happening steeper and steeper, so it must be speeding up. And we talked about looking at the slope of it. So if we do a case study and zoom in at the time 1 second, we can see that it almost looks like it's constant velocity. We know in general that it's speeding up, but if we're zoomed in just here, it looks like it's almost moving with a constant velocity. And so the way to think of this graph is the blue is showing what the object actually did. To talk about how fast it's going at 1 second, we're going to say the object starts speeding up, but what if hypothetically right here, instead of following the blue lines that it actually did, what if it was to stop speeding up? And if it was to stop speeding up, it would follow a straight line path. And so that straight line path is like the hypothetical position versus time graph that it would have followed if right at the moment 1 second it had stopped speeding up. So what we do is, instead of finding the speed that it actually was traveling at, because it's changing, we find the speed of this hypothetical line. And we can see if the particle had kept tracking this line, every second it would have moved 4 centimeters, and another second it would have moved 4 centimeters, and another 4 centimeters. And so the slope of that line is negative 4 centimeters per second. The negative because we have a negative slope, or you could say because the velocity is in a negative direction. So if we do this for the 1 second time, we get a velocity of negative 4, and we'd say for just that instant, it had that velocity, right? So we can continue doing that for another point. We could say, let's look at t equals 3 seconds, and we could say, all right, let's find the steepness of this line and say the velocity it has at that moment would be the speed of the hypothetical line that it would have traveled. And this line being a little steeper, for every 1 second, this line shifts down 12 centimeters, and so it has an average speed of negative 12 centimeters per second. If we do this at each and every point and carefully work it out, in this particular graph, we see it starts off with a flat slope, no speed, and it's becoming increasingly more negative by negative 4 centimeters per second each second. And so there's a sort of a pattern here that every second we wait, it's going 4 centimeters per second faster, but in the negative direction.